Welcome back, everyone. In this video, we are going to finish up our discussion on transformers and do one last example. And then we will finish up our introductory circuits course with an intro to devices. And we'll get to learn about how we can use diodes and transistors in order to be the building blocks of computers and other very cool electric devices. So let's go ahead and get started. So here's our goals for today. First, we will briefly review our transformer toolbox, and we'll do one last example about how to solve a circuit with a transformer. Then we will introduce semiconductors and diodes, and we'll see how diodes can be used as one-way valves to force current to flow in only one direction. Next, we will talk about ideal diodes, and we'll learn how to recognize whether ideal diodes will behave as a conductor or have non-conducting behavior. And finally, we'll learn about some very important applications of diodes, including using diodes for transistors and using transistors to build other kinds of electric devices. So let's start with a quick review question before we move on. In our previous video, you'll remember that we introduced transformers in the context of electric power delivery. One of the big applications for transformers in the real world is in order to help deliver electrical power from a power plant all the way to end consumers. And we learned a bunch of key terms about AC power delivery. If you'd like, take a moment and pause the video and see if you can correctly fill in these blanks. If you need, you can review these terms in our previous video. So take a moment, see if you can fill in these blanks. All right, so let's go ahead and go through them one by one. First blank, we have the power grid. The power grid is the network of transmission lines and substations which supply power. Next blank is transmission lines. You'll remember these are the things that carry electric current from a power station over long distances. Next are substations. You may remember from our previous video that substations convert our high voltage power from the transmission line back down to the lower voltages and end up distributing that power to customers. Next blank is single-phase power. You'll remember single-phase power is AC power transmitted using a single sinusoidal source. And finally, three-phase power. You'll remember that three-phase power contains three sinusoidal voltages generated 120 degrees out of phase with each other. And you may remember that most electrical power is actually generated and distributed as three-phase power for better efficiency and to help us deliver a constant instantaneous power. So definitely make sure you remember these terms as we review AC power. All right, so let's briefly review a few of the main points we covered last time. First, you'll remember we covered the maximum power transfer theorem for AC circuits. You'll remember that this theorem is very similar to maximum power transfer for DC circuits. And if you see any homework or exam question asking you about maximum power transfer, you should immediately be happy because that gives you a big hint about what equations you're going to need to solve that problem. You'll remember, in order to transfer maximum average power from an AC source to a load, we need the load's impedance to be equal to the complex conjugate of the Thevenin impedance of the source. Also, if that condition is met, we can predict that the maximum average power we'll be able to transfer will be given by this equation. So definitely remember this equation as you finish up our last homework problems. Last time we also introduced transformers and coupled inductors. You'll remember, a transformer is a device that couples two AC circuits magnetically. So instead of directly connecting one circuit to another with wire, we are using overlap of magnetic fields. And so we do this using two coupled inductors. You'll remember coupled inductors are two or more coils wound around a common core. And we wind our coils around the core such that the magnetic fields overlap. Since magnetic fields overlap, we call these coils magnetically coupled. You'll remember from physics class and Faraday's laws that if we have coils with overlapping magnetic fields, we can induce current flow between the two coils. And so, by using a coupled inductor, we can create these transformers, and very often we use them to raise or lower AC voltages when transmitting power. Finally, as we finish up our transformer examples today, make sure you keep our transformer toolbox handy. Remember, we assume, for the purposes of this course, that our transformers have ideal behavior, meaning that the coupling coefficient is 1. Assuming our transformers are ideal, we can use the following equations in order to solve for unknowns in our transformer. Remember, it's important to pay attention to the orientation of the coils. Depending on the coil orientation, the equations that you'll want to use will be different by a negative sign. It's also important to remember the turns ratio, which is the ratio of the coils in the secondary, number of turns in the secondary coil divided by number of turns in the primary coil. Additionally, remember we can replace a transformer with an equivalent impedance using the equation shown here, where this z of omega is the existing load, and we know that if we take that existing load, multiply by 1 over turns ratio squared, we can replace that transformer with an equivalent impedance. So before we move on, let's do one last example about transformers. In this circuit, we have a transformer. Notice it's an ideal transformer because of the 3 lines. And we see that we do not know the turns ratio of this transformer. However, we do know our voltage, and we know how much current is entering that load on the secondary coil. We are also told that this impedance is 10,000 ohms, and we're given this current I2. So first part of the question asks us to find our turns ratio, and then we want to figure out the equivalent impedance that the primary coil experiences, In the second part, our goal is to determine the equivalent impedance felt by the primary coil due to that 10,000 ohm impedance in the secondary coil. And then finally, our last part of the question is to determine the current I1 being supplied by the voltage source. So let's give this question a try. So first we want to determine our turns ratio, N. And I often find it helpful when doing these problems to just first take a moment and think about what we know. You'll remember in our transformer toolbox, we define our voltages V1 and V2 and our currents I1 and I2 following the conventions I've drawn here in red. And so let's just take a moment and ask ourselves, what do we know? Well, in this case, let's go through one by one. First, I1 is unknown. How about V1? Turns out V1 is known. V1 is just equal to our voltage source V because there's nothing else in the primary coil. So we know that's just 10 volts. What else do we know? Well, we know I2. In this case, we can write that I2 is actually negative 5 milliamps. Notice I put the negative sign there because of the direction. And then finally we have our voltage V2. Notice that V2 is not directly given. However, do we know enough information in this circuit to find V2? Yeah, notice in this case, for this particular circuit, we can find V2. And we can find it because I2 and Z load are known. So in this case, we can actually go ahead and solve for V2. We know that V2 must be equal to, we have 5 milliamps entering the load, so we'll go ahead and say 0.005 amperes. That's entering the load. So 5 milliamps is entering, and our impedance, Z load, is 10,000 ohms. So by Ohm's law, we can say that V2 is 50 volts. All right, so now that we've kind of looked at what we know and what we don't know, let's return to our original question in part A. In part A, we are looking to find our turns ratio, which is currently unknown. So let's take a moment and look at what we do know, and we can ask ourselves, is there an equation in our toolbox that we can use to relate something we do know to the turns ratio N? And so if you take a quick look at what we know and don't know, you'll notice that we know both V1 and V2. So a good strategy here is to use the toolbox equation Here we know we have that equation V1 equals N1 over N2 times V2. So we can use this transformer toolbox equation to find N1 over N2, and then we know that our turns ratio N will actually be equal to N2 over N1. So let's give this a try. Remember, we know from before that V1 is 10 volts, and we found that V2 is 50 volts. So from our toolbox, again, noticing our coils are both oriented with the dot on the top part, we recognize that V1 is equal to N1 over N2 times V2. That means 10 volts is equal to N1 over N2 times 50 volts. That tells us that N1 over N2 must be equal to 1/5. That means our turns ratio N, which is N2 over N1, that must be equal to 5. So we have successfully completed the first part of the question. Let's move on to part B. In part B, we are asked to find the equivalent impedance felt by the primary coil. Well, if you see that word equivalent impedance, does that make you think of any equation in our toolbox? Well, in this case, from our toolbox, we know that the equivalent impedance felt by replacing our transformer with an equivalent impedance, that equivalent impedance will be equal to 1 over N squared times Z load. So in this case, we just need to substitute in what we know. Z equivalent must be equal to 1/5 squared times 10,000 ohms. If we substitute, we determine that our Z equivalent is 1/25 times 10,000. And that gives us that our Z equivalent will be 400 ohms. Let's go ahead and finish up with the last part, part C. In part C, we want to find I1, the current supplied by the voltage source. There's actually multiple ways you could find this. The first approach would be to take advantage of the equivalent capacitance we just found in the previous question. In the previous question, we found that the transformer is equivalent to a 400 ohm impedance, so we could just use Ohm's law and our equivalent impedance. The other approach that works in this particular case is to use our current I2 and the turns ratio N to find I1 using a toolbox equation. In this case, I'm going to go ahead and use method 1. But if you chose to use the second method, you would get the same result. The only thing to be careful of is watch the negative sign, because our toolbox equations assume that I2 is going in the opposite direction, so you'd have to use a negative 5 milliamps if you choose method 2. Alright, so if I use method 1, then all I need to do here is to use Ohm's law. We know in this case that our current I is going to be equal to our voltage across our equivalent impedance divided by the equivalent impedance, which gives us 10 volts divided by 400 ohms. 10 divided by 400 gives us 0.025 amperes, or 25 milliamps. And there you have it. Notice that these transformer questions are really pretty easy once you get the hang of using the transformer toolbox. So definitely go back through and practice this example. And if you need, make sure you check out our examples in the previous video. And keep that transformer toolbox handy as you finish up our remaining homework questions. So let's now move on to the last new topic for this course. This course is just an introduction to circuits and devices, so we're not going to go into tons of detail on semiconductor devices. But I hope you find this introduction interesting, and if you have the opportunity to take more advanced courses, you'll get to learn much more about semiconductors and electrical devices. So let's briefly spend the rest of the course introducing semiconductors and devices and learning how we can use all the tools we've covered so far to create the building blocks for diodes, transistors, and even computers. A good place to start is with these key terms. You may remember learning about semiconductors in physics or a material science course. And when we talk conductors or insulators, basically the thing we want to ask ourselves is, does the material allow electrons to flow freely? Conductors are materials which do allow electrons to flow freely. Typically what this means is that the valence electrons are not held very tightly. So metals and materials with loosely bound electrons generally have conductive properties. Insulators, on the other hand, are materials where electrons cannot flow freely. And very commonly, these are materials such as glass or nonmetals. Rubber and plastic are also generally insulators. These are materials that tend to hold on more tightly to their valence electrons. Finally, we have a third category known as semiconductors, and these are materials that have electrical conductivity in between a conductor and an insulator. And the interesting thing about semiconductors is that we can change the conductivity by doping the material with a second additional material. When we say doping here, what we mean is that we are forcing additional atoms into that material's crystal structure. And when we do this, we can gain some new properties. The material that we force into the crystal structure is called a dopant. So in this context, a dopant is a new material added to a semiconductor in order to change the properties. Alright, so when we talk about semiconductors, it's first important to distinguish between p-type and n-type semiconductors. The first type we'll cover is n-type. In this example, we're specifically talking about n-type silicon, but the element here could also be germanium or some other semiconductor element. We're not limited just to silicon. In this case, we call the silicon n-type because n stands for negative. So n-type silicon is negative because there are extra electrons present. You might be thinking, well, where do these extra electrons come from? What we do is we add pentavalent atoms, such as phosphorus, into the silicon. And pentavalent atoms like phosphorus have 5 valence electrons. So adding phosphorus creates an extra electron in the crystal structure. And so this extra 5th electron here is not bound within the silicon crystal, and therefore this extra electron can move around within that silicon material. And because we have these extra electrons, the n-type silicon is overall slightly negatively charged. So we call type P silicon p-type because P is for positive. In this case, instead of having extra electrons, we create what's called empty holes in the material. And so in p-type silicon, we add trivalent dopants. These are atoms with just 3 valence electrons. So for example, we could choose to add boron, aluminum, indium, or other atoms which contain just 3 valence electrons. And when we add these atoms into our silicon, you'll see that because there's only 3 valence electrons and not 4, we create a hole where a missing electron should have been. And so that dopant will create a hole or a vacant spot where an electron should have been located, but there isn't one. And since electrons can move around, these holes can also move around within our silicon material. So on average, p-type silicon will be slightly positively charged because of the presence of these holes. So how does this actually help us make circuits and devices? Well, it turns out if we combine a p-type semiconductor and an n-type semiconductor together, we can create a device called a diode. And a diode is a device which contains a p-n junction and electric contacts at its terminals. So essentially what that means is we take some p-type semiconductor and n-type semiconductor and we combine them together. And this creates what we call a p-n junction. And when we combine these two layers together, notice what happens at the interface between the p-type and n-type material. At the interface, the electrons and holes can migrate across the p-n junction and recombine. So in this case, the positive holes and negative electrons can combine and create this effectively neutral area. And so this creates what's called a depletion layer. And we'll see that this depletion layer actually acts like a one-way valve. And so this allows us to create these diodes, and we're able to force current to flow in only one direction. And so the reason for this is because the recombining of the electrons and holes in this depletion layer will allow us to create a sort of valve for our current. Let's take a closer look at diodes. And in this case, it's very helpful to use that water analogy. So if we use a water analogy here for our diodes, we can treat a diode to act like a one-way spring-loaded water valve. Something like in this picture. And you can see that for this spring-loaded water valve, we need to apply some minimum positive pressure in order to force that valve open and allow water to flow through. In this first picture, we don't have enough pressure on our valve, and so currently that valve is shut. This corresponds to the situation where we don't have enough voltage applied across our depletion layer in order to make our electrons flow. So we need to apply enough positive pressure or positive bias voltage in order for water or current to flow through this one-way valve. In the second picture, you can see what happens if we apply enough pressure. The spring-loaded valve will be opened and will be able to flow through the diode. And finally, the interesting case is also this third case where we have the reverse happening. So you can see what happens here is if we have zero pressure or negative pressure, notice that this valve does not allow flow in the backwards direction. So similarly, if we apply zero or negative voltage across our diode, no current will flow through that diode. And so the thing that's actually acting like the spring-loaded valve in the actual diode is that depletion layer. The depletion layer is the thing that allows us to create this one-way valve for our current. So let's talk a little bit more about ideal diodes. Typically, for the purposes of this course, we like to assume our diodes have ideal behavior. And so, in order to tell whether a diode has ideal behavior, we should first check our symbol. An ideal diode will have a black symbol, similar to shown here. The positive end of the diode is called the anode, and that is the end that has p-type silicon. The negative end of the diode is called the cathode, and that end is made out of n-type silicon, or an n-type semiconductor. And then in the diode symbol, this line that we see that could be a horizontal or vertical line, depending on the diode symbol's orientation. This line indicates the area where the cathode is. So if you look on a circuit diagram, you can see whichever end corresponds to that line, that is our cathode, and then the anode is the opposite end. So let's talk a little bit more about the behavior of a diode. And so it turns out that we can change the behavior of our diodes by applying what's called a bias voltage across the p-n junction. And so essentially what's happening here is depending on what voltage we apply on our diode, we can encourage current to flow forward or backward. So let's briefly remind ourselves of a few things as we talk about diode behavior. Our first thing to remember is that current flows from high voltage to low voltage. And specifically for a diode, we generally want to make our current flow from that hole-rich P region to the electron-rich N region. So therefore, we generally want to apply some positive bias voltage or positive voltage across our diode, like shown here. So in this case, forward bias means applying a positive voltage across the diode, causing our charge to flow through. So in the forward bias region, we are applying some positive voltage. Some positive voltage is being applied across our diode. Again, remember the P region is on positive end, N region is on the negative end, and we see that when we apply forward bias or positive voltage across this diode, then we will allow current to flow through. And you see that once we have applied that minimum forward voltage required, we are able to see current flowing through the diode. Let's now talk about reverse bias. So again, here this is forward bias. In reverse bias, we have the opposite case. So in reverse bias, we're applying a negative voltage across the diode. So in this case, we could either write our VD like this, where VD is less than 0, or we could swap the polarity. When we have reverse bias, it turns out that this actually turns off the flow of current through our diode. And the reason why, of course, is, as we saw in our previous slide, we see that when we have reverse bias, it forces our spring-loaded valve shut. Essentially, we do not have enough voltage to push a positive charge across the depletion region and back in to the P-type region. So therefore, reverse bias means applying a negative voltage across the diode, and that prevents flow through the diode. As we mentioned, there is a minimum positive voltage required in order to turn on our diode, and that is called the forward voltage. You see that indicated with a sort of knee in the IV curve of the diode. And we see that depending on the material, for example, for silicon, it's around 0.7 volts forward voltage required. For germanium, it's a little bit less. Also notice what happens in the extreme case where we apply a very large reverse bias voltage. At a certain point, if we apply enough reverse voltage to our diode, we will cause what's called this avalanche behavior or breakdown voltage to occur. And basically, this will essentially force current to flow in the reverse direction and potentially damage our diode, but it would actually enable current to flow in the reverse. So if the reverse bias voltage is more than this breakdown voltage that we see here, then we will be able to have negative current flowing through our diode. So you may remember seeing this equation in some of our labs, where we can actually predict the amount of current that a diode will allow to flow under forward bias conditions. And so the amount of current that's able to flow through is called the diode current. And often we can simplify this equation, assuming that this reverse saturation current is relatively small. We can simplify this equation down into an exponential relationship. And so we can see that the amount of current that flows through our diode under forward bias will flow exponentially larger until eventually we reach some maximum point. So let's briefly revisit ideal diodes. We mentioned earlier that for the purposes of this course, we generally assume that our diodes are ideal unless otherwise stated. So an ideal diode has a black symbol on our circuit diagram, so it will look something like this. And we assume that the behavior of this ideal diode depends completely on our bias voltage. So remember, the bias voltage, or VD, is basically the voltage from the p-type or positive side to the n-type or negative side. So if this voltage VD is greater than or equal to 0, we assume that our ideal diode is conducting and acts like a short circuit or plain wire. However, if our bias voltage VD is less than 0, we assume the diode is not conducting and acts like an open circuit or a broken wire. Notice that this is an approximation because normally we require our VD to be greater than about 0.6 volts in order for the diode to allow flow, but for an ideal diode, we go ahead and just assume as long as our bias voltage is positive, then current will flow through. So ideal diodes are a very convenient way to simplify the behavior of diodes and make approximations. But of course, depending on the application, these assumptions may not give you a perfectly accurate result. So they're good for simplifying, but in certain situations, we may need to go back and use the more detailed diode equations and detailed IV behavior. Let's go ahead and try a quick example. Suppose we have this circuit shown on the right-hand side here. And suppose we are given that V1 is 0 volts, V2 is 5 volts, and V out is 2 volts. The question here is to determine whether each diode is conducting or not conducting under these conditions. Let's go ahead and assume the diodes are ideal because of the black symbol. And let's also remind ourselves that as long as our bias voltage is greater than or equal to 0, then we will have conducting behavior. If our bias voltage is less than 0, we will have non-conducting behavior. So in this example, our goal is to determine what is VD across each of these diodes. Remember, VD is the voltage difference between the anode and the cathode. So if you'd like, go ahead and pause the video and see if you can correctly calculate VD of diode D1 and diode D2. Take a moment and give it a try. Well, let's go ahead and take a closer look at this. You'll see that this calculation can actually be done pretty quickly just by looking at these values. For diode D1, we see that on the left side, on the anode side, we're sitting at 0 volts. And on the right side, we're connected to V out, which is sitting at 2 volts. So in this case, what is VD? Well, VD is going to be 0 volts minus 2 volts, or negative 2 volts. So in this case, will VD for diode 1 be conducting or not conducting? Well, in this case, since VD is less than 0, D1 is not conducting. How about D2? Well, D2, on the cathode side, we're sitting at 2 volts still, because we're connected to V out. But on the anode side, we're sitting at 5 volts. So in this case, for diode D2, we're sitting at 5 volts minus 2 volts, or plus 3 volts. So in this case, we see that D2 is conducting, since our VD is greater than 0. So therefore, correct answer for this example is choice D. We see that because diode D1 has a negative bias voltage, we determine D1 is not conducting, whereas D2 has a positive bias voltage and is therefore conducting. Remember, for an ideal diode, as long as the bias voltage is not negative, we assume we are conducting. Let's briefly review a few applications that you should be familiar with related to diodes. Many of these are already probably familiar to you. For example, there's LEDs, solar cells, half and full wave rectifiers, and finally transistors. You may be familiar with LEDs because they're extremely common in many electric devices. And the idea of an LED is, rather than being a plain old diode, this diode has the additional property that it is a light-emitting diode. So LED stands for light-emitting diode. And essentially what happens in the LED is that when electrons and holes combine, the electrons will actually release energy in the form of light. And so depending on how much energy is released, you may remember learning that formula E equals h nu from chemistry class. If you know your energy, you know Planck's constant. And then if you know nu, this is the frequency of the light released. And so depending on the amount of energy and the band gap, basically the material property of that LED, you can actually tune the LED to release different colors of light. You can check out some of these references for more information on this, but LEDs are a very important application of N-type and P-type semiconductors. Another very important application is solar cells. The animation here is a nice illustration showing essentially what's happening. In a solar cell, sunlight actually creates electron-hole pairs in silicon. So essentially what happens is we create more electrons in the N side, and we create holes in the plus side, or in the p-type side, and we can generate current when we allow those holes and electrons to recombine. We also introduced rectifiers in our lab. And you might remember that rectifiers use diodes and their one-way valve behavior in order to force current to flow in just one direction. And this animation basically illustrates what's happening in the half-wave rectifier, where in a half-wave rectifier we are basically only allowing the positive portion of our voltage through, and then the negative or reverse flow is blocked. But then we also have full-wave rectifiers, and you may remember that bridge circuit we looked at in the lab, where we can actually force an AC input to turn into a positive DC output. So there's lots of really nice tutorials and animations of this online, so you can definitely check those out if you'd like more examples. And you may remember that you can also add filters in order to help stabilize this output and turn it into a flatter DC signal. Finally, another really important application of diodes is creating what we call transistors. Transistors are interesting because they're actually a three-terminal semiconductor device. So instead of just taking a diode with maybe a P and an N region and two terminals, we instead create this transistor that has a third terminal. And so you see we have a collector, a base, and emitter. So transistors are actually made by stacking not two, but three layers of P or N-type semiconductor materials. Notice that a plain old diode is just two layers for a P-N junction. But a transistor is made using three layers. So we can have PNP or NPN. And in this case, no matter the type of transistor, we generally label the terminals as the collector, the base, and the emitter. I like to call the collector analogous to a holding tank, which basically stores water or stores charge. We have a base that basically is like our control valve, which controls how much current can flow through. And then the emitter is basically the place where the output exits. So it's very common to use that water valve analogy as you work on transistors. We'll cover this more in just a moment. So when you hear the name transistors, you may have heard of a lot of the different companies that build electric chips. And when you hear the word transistor, you might even associate a transistor as one of the building blocks of chips today. So today's semiconductor chips generally contain millions or even billions of transistors spaced only a few nanometers apart. And generally, the more transistors we can fit on a CPU or on a computer chip, the more computing power we can get. And so you may have seen these competing graphs between chip companies like Intel and TSMC, and everybody's trying to compete to ramp up the next technology and have more and more transistors on their chips. It turns out there's actually two main categories of transistors. First type is called the bipolar junction transistor, or BJT. Second flavor is called field effect transistors, or FET. So, bipolar junction transistors actually use current to control the flow. So, they're analogous to having a current-controlled valve, and we still have the collector, emitter, and base terminals. But you see, essentially what's happening is we have this current that is basically pushing on our transistor, and that controls how much current we are able to flow through. Field effect transistors work in a similar way, except rather than using current to control the flow, they use an external electric field. Instead of calling it collector, emitter, and base, we call the terminals source, drain, and gate, but the function is pretty much the same. We have our source, our drain, we have our gate, just like how we have the collector, emitter, and the base. So you might remember back in the beginning of the course we talked about dependent sources, and these are basically real-world dependent sources. The amount of flow or current we get through a transistor is dependent on the control current or control voltage elsewhere in that transistor. So, depending on the voltages at each terminal, our transistors can actually behave in one of 4 different modes. Here we will focus on the behavior of the bipolar junction transistor, but similar behavior can also be seen in our field effect transistor as well. So our goal here is to just briefly introduce this behavior, and if you take more advanced courses, you may learn even more details about these transistors. So, depending on the voltages at each terminal, our transistor behavior can operate in one of these 4 modes. First is cutoff, saturation, third is active, fourth mode is reverse active. Let's take a closer look at each of these cases, and we'll use that valve analogy to help us understand what's going on. So, first mode of operation for our transistor is called cut off. And in cut off, it's basically what it sounds like. In cut off mode, the transistor is completely shut off. So, it's as if the valve is closed. And so, a transistor in cut off operation will act like an open circuit between the collector and emitter, because nothing is allowed to flow through. And in this case, in order for a transistor to have cut-off behavior, both diodes have to be reverse biased so that no current can flow through. So if we label our voltages for our collector, base, and emitter, we see that to be in cut-off mode, our collector voltage must be greater than our base voltage, and our emitter voltage must be greater than our base voltage. So basically, this forces our diodes to not be allowing anything to flow through. And one other thing to note, this description is for an NPN transistor. So basically for a PNP transistor, you would just have to reverse the polarity or the greater than or less than signs in this slide. All right, our second mode of operation is saturation. And in saturation mode, the transistor is fully switched on and flow is maxed out. And so in this case, the transistor will act like a short circuit or a plain wire. And the reason for this is because there's basically unrestricted flow. And in this case, both of the diodes of that transistor are forward biased. And so in this case, for the NPN transistor, we see that our bias or our base voltage VB will be greater than our collector voltage, and our base voltage will be greater than our emitter voltage. So we see that since both diodes are forward biased, the current will flow unrestricted through our transistor, and therefore we get that plain wire behavior. Our third mode of operation is called active. Generally, this is the mode of behavior that we want our transistors to be in. Most of the time, we design our transistors to have active behavior. The reason why we like active behavior is because in active behavior, our transistor behaves like a linear amplifier with a fixed gain beta. In order for us to have active behavior, we actually have reverse bias behavior in both of our diodes. And essentially what this does is this allows current to flow from our collector to our base, but then we can control how much of that current is allowed to go through to our emitter. So you may remember when we covered dependent sources in the beginning of the course, we talked about how dependent sources are a lot like a faucet, where we turn the handle to control the flow. So the real-life physical version of this would be our transistor in active mode. In active mode, we can control how much flow we allow by controlling the amount of current at VB, at our base terminal. Finally, the last mode of operation is what's called reverse active. Reverse active is actually the opposite of active mode. Generally, this is rarely used in real life. It's pretty much the opposite of normal operation. So this would often happen if something is actually wrong or there's some problem with your circuit. Generally, we don't want reverse active mode to happen. In order for our transistor to be in reverse active mode, we see that the emitter voltage is greater than the base voltage, and the base voltage is greater than the collector voltage. In this case, our current is actually encouraged to flow in the opposite direction. It flows from the emitter back up to the collector. We still get a little bit of amplifier or dependent source-like behavior, but typically in this case that beta value is much smaller than in active mode. And again, the flow is going the opposite way we want, so generally this is not useful. Please make sure you remember these 4 modes of operation. And it's very helpful to remember which mode is which, and drawing pictures of these valves can also help illustrate. Basically, by looking at the different voltages, you can figure out which direction the current must be flowing. So definitely remember these voltages and these modes of operation. And let's try some quick examples, just to help everyone practice. So in this example, let's suppose we have an NPN transistor with the following operating conditions. I'll go ahead and label them on this figure. We're assuming our collector is sitting at 5 volts, our base is sitting at 8 volts, and our emitter is sitting at 1 volt. So a question here is asking, which mode of operation are we in? In this case, it may be helpful to draw a picture to better visualize what's happening. Notice our base voltage is greater than our emitter voltage, so since current wants to flow from high to low, current will want to flow from the base to the emitter. But notice the collector and base, actually current will be discouraged from flowing that way. And so what you can see is happening in this case is because our base is greater than our emitter, we will have some sort of flow happening. You'll notice that there is basically some bottleneck here between our collector and base voltage. That 5 volts is actually going to be discouraged from flowing through. There's going to be a bit of a bottleneck because this 8 volts is higher. Therefore, in this case, if you look back at our rules, you'll see that in this case, we are actually in saturation mode. We have, in this case, our flow is maxed out, and our current will flow unrestricted from the collector to the emitter. In this case, the transistor will behave like a short. Let's try one more example. Here we have an NPN transistor, and we have the following conditions. Collector voltage is 1 volt, base voltage is 8 volts, emitter voltage is 10 volts. This question is asking, what operation mode is this transistor in? In this case, it's helpful to just look straight at the voltage values and notice what direction the current will want to flow. In this case, I'm going to want to flow from high to low voltage. So in this case, my current's actually going to be flowing in the opposite direction, from the emitter back up to the collector. So in this case, I'm actually in reverse active mode. That's because my emitter voltage is greater than my base voltage, which is still greater than my collector voltage. In this case, because the voltages are set the way they are, this transistor is actually going to be sending its current in the opposite direction as we would normally desire. So why do we bother to learn about transistors? Let's go through a few more applications of where transistors are used. And one of the biggest applications is what's called an integrated circuit. An integrated circuit is a collection of electronic devices integrated or interconnected on a single silicon chip. As we mentioned, rather than building everything on a breadboard or having a pile of spaghetti-like wires, having everything fabricated and etched on a silicon chip, that makes our circuit a lot more compact, a lot more robust, and often it makes it a lot more efficient to fit into other packages. So many times we want to actually take our circuits and fabricate them on a silicon chip rather than just connecting a bunch of wires together. We learned before about analog and digital signals when we briefly introduced these. You'll remember that analog signals can take a wide range of potential values. the signal is proportional to a physical quantity. For example, a temperature sensor's voltage could have a range of values depending on the temperature. So when I see the word analog, I like to think analogy or proportional to. On the other hand, digital circuits or digital signals can only take a finite number of values. For example, a binary signal on a computer will be either a 0 or a 1. Binary signals are signals that can take only one of two possible values. So definitely make sure you remember these terms. They do come up a lot when you work with transistors and circuits. Another big application of transistors is computer architecture. Computer architecture is a broad term which refers to the design and organization of components making up a computer. And it can also refer to approaches for processing data and transferring data. As you might imagine, there can be entire courses and textbooks and whole disciplines dedicated to computer architecture. So, for us in this course, we don't have time to cover all of it, of course, but we will briefly introduce computer architecture topics, and so definitely make sure you check out our labs and our supplemental materials for more information. Really, the key takeaway you should remember from these devices slides is that by combining transistors, diodes, resistors, and digital logic circuits, we can create these one-way flow valves, we can perform calculations, and we can even create memory and build computers. So there's a lot of really powerful stuff you can do with computer architecture. So if you take additional electronics or electrical engineering courses, you'll have the opportunity to learn much more about computer architecture. In this class, we will briefly introduce computer architecture in our last video, and we'll also try some of the topics in our last labs. So definitely check out our labs and our supplemental materials for more information. So let's go ahead and wrap up here for today. You should now be more comfortable solving transformer problems and understanding the applications of magnetically coupled circuits. You should also now recognize semiconductors and diodes and how they can be used to force current to flow in only one direction. Make sure you also remember how ideal diodes work. Remember, as long as an ideal diode has non-negative bias voltage across it, then it will be able to have conducting behavior. Otherwise, if we apply a negative bias voltage across the P and the N terminals, then the diode will have non-conducting behavior with that negative bias voltage. Finally, we've introduced some very important applications of diodes, transistors, and devices. As we wrap up the course, we will take one last look at devices and computer architecture in our next video, and then we'll finish up with exam review. Thanks everyone for joining the fun, and we'll see you in the next video.